Welcome, Timothy. How are you doing today?
I'm very good. Thank you. Thank you to invite me here.
Yeah,
It's exciting and see what kind of information I can share with the audience.
yeah. Thank you so much for sitting with me. I really appreciate it. And I know we're talking about the Gen 3 Dual 3 series, right? So,
Okay.
but maybe we could start off more bigger picture. And you could start off by describing a bit of SemiQ's history. How it started and some of the key product portfolios.
Okay. So let me try to share my screen and
Yeah,
maybe audience have a better understanding. Okay. Can you share my screen?
yeah. I can see it. Yeah, I can see the
Okay.
timeline.
Okay, great. So the SemiQ established about 18 years ago in 2008 as a pure silicon carbide power semiconductor player. So until 2019, almost 10 years, is the early commercialization period. We grow the epi and we used the foundry to develop the diode and the early generation, the MOSFET. But the actual industrial and commercialization happening from 2020, about 6 years. So we, as a fabless foundry company, we used so far is three different wafer fab, one in North America, the other one in second one in actually Scotland, and the latest, the third one is in Taiwan.
Mm-hmm.
So we develop our own silicon carbide MOSFETs and the diode with the SemiQ brand. And then we use that the bare die into the discrete package or inside the module. So SemiQ is providing the different type of device format to the customer. So for example, here is our product portfolio. We have a diode MOSFET and modules, and also we have a non-good die, both diode and the MOSFET. Those are our product portfolio. And so if you can see, here is the power module product portfolio.
Yeah, I see.
We have a generation 2, generation 3 version of die inside of, you can see the 6 different of package.
Yeah,
So yeah, depend on the power rating and the topologies. So we provide a single switches, page lag, full bridge, and three-phase modules. And today we may focus on our S4 is the QSiC Dual3 module product. That's industry standard package and designed for the IGBT in the early stage. But we improved the internal design and power carrying capability and provide multiple options. Yeah,
yeah.
so that's where we are.
Thank you. Thank you for a bit of the background and product history. Maybe we could focus on the QSiC Dual 3 range because that's the most recent one, and there was a press release at PCIM about that as well. Maybe you could briefly discuss some of the key aspects of the new product line.
Yeah, the QSiC Dual 3. So we are offering about you see 1200 volt, six product, and less than 2 months we will release 1.7 kV. It's already in assembly right now, and we provide early engineering sample no later than end of August to the key customer.
Yeah,
And around the September timeline, we will upload to the public domain.
gotcha.
Yeah, so the QSiC Dual 3, so the SemiQ products, 1 million part. is right now is the highest power density in the open market with the same package. And
Mm.
yeah, we accommodate the latest versions of the technology here. Yeah,
Mm.
so we expect well, actually we have a lot of interest from industry as of today.
Yeah, actually, maybe we could talk about, how you're able to achieve that high power density. As you were saying, maybe we could zoom into the modules at the device level, the dual three modules. They use the Gen 3 silicon carbide MOSFETs. So maybe you could describe that new generation in more detail. Does SemiQ use a trench or planar architecture? Did Gen 1 or Gen 2 use different architectures? What was sort of the timeline or the movement from Gen 1 to Gen 3, and what were the advancements there?
Yeah, so SemiQ, as of today, we are developing generation 4 actually. But the generation 3 was released, the device released in end of 2004. Now it's close to 18 months or 2 years, nearby 2 years. So generation 3, generation 2, all SemiQ process is a planar process, it's not a trench device.
Okay.
And you can see generation 3, the R1 SP is about 30% improvement compared to Gen 2. And the
Yeah.
gate threshold voltage also increased to 2.5 to 2.8 to up to 3.5. And the gate voltage also reduced from 20 volt to 18 volt. And we also have a strong advantage is a turn-off loss, about 30% improvement, and the reverse recovery charge also improved. So these Gen 3 is automotive level qualification is done, and we offering into the market in the bare die and discrete and the power module. So we incorporated this generation 3 version of die inside the QSiC Dual 3 module.
Hmm. Um, thank you for that information. Um, Maybe we could move towards. I am curious to know the improvements in the planar architecture. Um, if you have any more detail there, I am curious.
Yeah. So the Gen 3, we have a unique cell structures and very solid edge terminations. So our goal is really from the design and the screening process, no failure in the field is our SemiQ philosophy and the strategy in behind.
Mm,
So the cell density is important,
mm,
and it also data design is also process partner, what kind of the process resolution they providing to us. So it's this device developed over 3 years ago, but it's the key is robustness of
mm,
device in the field. Yeah,
mm.
so that's how
Yeah.
we do it. Yeah.
Gotcha. And speaking of the robustness, the dye screening via the wafer level gate oxide burn-in, maybe it'd be helpful to start with some fundamentals there. Some of the common interface issues with silicon carbide, including carbon clusters and near interface defects. How do they impact the gate oxide over time, and how does SemiQ address those challenges in their Gen 3 devices?
Yeah, so if you see it, before we get jump into that questions, if you
Yeah.
see this detailed design of inside our QSiC Dual 3 module on the top left corner, so we use a 5 millimeter by 5 millimeter MOSFET die
Mhm,
and 14 MOSFET in parallel. And
mhm,
you also have a 50 ampere, 1200 50 ampere diode, 11 diode in parallel in single switch location. So it's a
mhm,
total, you can see 28 MOSFET and 22 diode. So it's a total 50 chip in a single module.
Yeah.
So it's a huge density, and if the single device fail, you have to trash the module, and the single diode or switch fail at the end, your system fail. So
Mm.
the screening out
It's very
the
important.
potential weak device is extremely important, and that's why SemiQ build up the wafer level screening process.
Mm. Mm.
So we developed a wafer level burn-in and screening process quite a long time ago. It's over 5 years.
Mm.
So we developed our own wafer level burn-in system. You can see in the bottom of the screen.
Yeah.
And so it's all the die and the gate source is using the pogo pin and touch to the gate source whole vapor at a high temperature. The vapor holding choke temperature increased to 150 to 175, depend on the conditions.
Okay.
And gate bias applied way over 35 volt, and
Mm.
we exposed at the high temperature and high gate bias for quite a long time. And then depend on product portfolio, we have different burning conditions. That's the SemiQ proprietary information, so I cannot share with you.
Mm.
So the gate burning process and any potential weak gate oxide or any kind of defect, like a particle induced or whatsoever crystal defect induced. So we screen out the potential weak gate device 100%. I think that's the bottom line. And
Mm.
if you see here, so once we have any MOSFET 100% gate burn-in testing, and then the DC vapor probe testing, and then dicing, and then 100% visual inspection, and packing and ship to the customer. This is a standard process. And we're shipping the die it is called our phase one known good die. It's
Okay.
a select only good device in the N by M array in the UV tape, and shipping to the customer or put into the module. And also we do select each good die inside the tape and reel.
Okay. Okay.
Yeah. So this is a non-good die program, but
Mm.
a lot of other case customer just want wafer itself and want to see the XY coordinate and also the probe data. So it depends on the customer's applications.
I see. They could
We
do
provide
tapering
that.
rail or the wafer. Okay.
Yeah, yeah, that's how we do it.
Okay. Um, so maybe we could talk about the drain source voltage screening. I know we just talked about the gate oxide and the burn-in testing. What's the significance of the drain source voltage screening exceeding, I saw this in the press release, exceeding 1,450 volts? And how does that relate to industry standards like JDEC or AEC, the automotive qualification? Um, why is that specifically mentioned in the press release?
So what we're doing is we are actually doing the generation or phase two wafer level screening. So phase two level is not just the wafer is testing in the gate oxide, and we tested at drain
Okay.
source. So in high temperature, high drain bias, we screen out any potential weakness in the either active area or edge termination area with a high reverse bias conditions.
Okay.
So we have two step. First step is we test in the room temperature, industrial grade. So we measure the reverse leakage 1 milliampere and then apply the negative bias. So any device which has less than VDS is 1440 or 1450, we screen out. even
Mm.
though our device spec is 1200 volt, with screening the it's not avalanche conditions, but at least 1 milliampere leakage level, we're checking the reverse voltage. And
I see.
that's the called it's the high voltage reverse bias testing. And our phase two, the implementation is here. This is a automotive IATF 16949 certified backend processing platform in Malaysia.
Yeah.
And we test the wafer at high temperature reverse bias conditions and then screening the die. So it's a wafer level process, a burning process is not just the room temperature and high reverse bias condition at high temperature, high reverse bias conditions.
Okay.
That's what
Okay.
we're doing.
Okay. Okay.
And so this is implemented in full production. And the third one we are under development is really called SemiQ KGD. Is a different level of KGD is a single die. After the slicing and then single die is a testing in the optical inspection, and then in the room temperature and the high temperature, AC switching testing, DC parameter extraction, and then each die also have a UIL testing. So it's a avalanche breakdown testing.
Okay. That's avalanche
And
breakdown.
then
Okay.
post six-axis AOI, and then die sorting into the wafer pack or reconstruction M by M array or tape and reel. So this is through really very high-end true KGD process. So we
Mm.
are almost finished the development, and then we start to apply this process for that like a QSiC Dual 3 type of a high density power module application.
I see. And that this slide here, that's phase three. So you had phase one, phase two, and phase three. Am I
Correct.
correct? Okay.
Yes.
Okay.
So it's a phase one, two is completed in production, and the phase three is under development. So these are the what we're doing, but it is
Mm.
also proprietary, so we may move on.
Okay. Okay. Uh, I was curious about the because you said that you do the 14 1450 volts for the 1200 volt devices. What about the newer 1700 volt devices? What are they
So
being tested?
1700 volt device, gate oxide burning process is exactly
Mm,
the same. There's no
mm,
difference.
yeah.
Even we also apply to 2.3 kV, but the drain burning still have a challenging for higher voltage. So we are working on to improve that drain source burning process at high temperature. But
Yeah.
testing, room temperature testing at the 1 milliampere leakage level, it's like around 2.2 kV, 2.3 kV is not an issue. So it's in process.
Okay. Okay.
Yeah.
Gotcha. Well, I see you have the slide ready. Okay, for the next question. Uh, the dual three family. We'll talk about sort of the module level. You know, factors. You've got the MOSFET only, the parallel SBD or Schottky barrier diode versions, the standard package versus the new aluminum nitride, the slash TIM high thermal options, and now you got the 1200 volt versus the 1700 volt devices. There's a lot of different options within this line. What fits what best. With
So
yeah,
yeah, so
application wise.
we look at the industry requirement. So the conventional industry, they are always fighting between the baseline is efficiency versus cost.
Mm.
So that's the reason why they continuously use IGBT module, because IGBT module provide a reasonable power conversion efficiency and with a lower cost. But AI data center is a significant change the power conversion efficiency requirement
Mm.
because industrial driver usually running about 8 hours, 10 hours per day. But AI data center running at full power in 24 hours, 365 days. So
Yeah.
the conversion efficiency is so important.
Mm.
And so we try to maximize the power conversion efficiency for those kind of applications. So highest conversion efficiency and the lowest heat dissipation requirement. So by adding the silicon carbide the parallel diode inside the module, so you can see the overall switching loss is reduced. It
Mm.
mainly because of reverse recovery charge reductions. And also the Schottky barrier diode, it has constant or fixed junction capacitor only. So the reverse recovery charge is independent to temperature or slew rate. So you can see on the left side is with the silicon carbide diode, and the right side is without silicon carbide diode. So it's a
Mm.
GCMS is with a diode, GCMX is without diode.
I
So you
see.
see the total switching energy is absolutely is below 50,000 micro. So it's a 50 millijoule. And then this is higher than 50 millijoule, even at room temperature. But when temperature increase, junction temperature increase, this switching loss is increased to over
They,
60,000, right?
yeah,
But it
quite
is
a lot.
still keep it's close to 50,000. So it's
Mm.
basically about 20% of
Mm.
reduction of your switching loss over temperature. So it's a
And
lower,
no, please carry on. Sorry, sorry.
yeah, lower switching loss you can achieve with a silicon carbide diode inside the module.
Gotcha.
And
And
also,
yeah,
yeah,
yes.
and
No, no, no,
also
please.
silicon carbide diode, like a freewheeling current when the module is running in the like a regenerative braking conditions.
Mm.
So sometimes they need a freewheeling diode current, depend on applications.
I see.
Yeah,
I see. Thank you for that. That's very helpful to know. And you were saying the modules, um, the 250 kilowatt modules, they'll have 11 diodes and 14, well, actually 22 diodes and 28 MOSFETs in total. So this is, and that helps with, as you were saying, the reverse recovery charge, keeping it constant over temperature and switching frequency.
yeah.
Gotcha.
Yeah,
Oh,
and
yeah.
we apply the aluminum nitride version too, right?
Yes, I was going to ask about that. You've got some with aluminum nitride and some with the pre-applied thermal interface material. How does that improve the thermal performance of the module versus the other products in the portfolio?
Yeah. So in the beginning, we start to use zirconia of the alumina substrate,
Yeah.
and you can see this is thermal simulation result of aluminum nitride. Is a much better thermal conductivity, 100 watt per meter Kelvin versus zirconia doped alumina is
Mm.
24 watt per meter Kelvin. It's a huge difference.
Oh, yeah, that's
So
massive.
even though GTA substrate is about 0.32 millimeter thin layer, and aluminum nitride is about uh, 62 0.62
So
uh,
double the thickness
yeah, a
almost.
double
Yeah.
thickness.
Yeah.
However, the thermal conductivity, you see the quite significant depth difference
Yeah. It's
with a
more than
different
double.
solder thickness here, almost double, right?
Mm.
So by doing that, you can reduce even the same power loss condition, the junction temperature of the chip, you can reduce another 20 degrees C
Mm.
or cooler.
Mm.
Or if you want to have like the same uh, junction temperature, it can carry on the more power. So it's about
Mm.
28% improvement of a power carrying capability. So the
That's quite
system
significant.
designer point of view, either you can reduce the heat sink size or cooling fan kind of things, or you can increase the power density. Either you improve efficiency or you increase the maximum driving power. So
Mm,
it's a so end users, system developer have a much more room. Either they improve the power conversion efficiency or much easier to managing the heat problem.
I see.
Yeah.
Oh, thank you. I was I wanted to kind of shift a little bit. I don't have any further questions here. Was there anything else that you wanted to add?
No, so you may mention about
The IGBT. Um,
yeah, well,
yeah.
how we can minimize the conversion from IGBT to silicon carbide
Yeah.
MOSFET.
Yeah,
Yeah.
that was in the press release, the dual three family is a drop-in replacement for IGBTs with minimal redesign. What does that mean practically? And, what aspects would a designer who wants to shift from IGBT modules to silicon carbides typically have to consider? And what makes the dual three family easier to drop in?
Yeah, so the bottom line is the package outline is exactly the same. So there are bus bar design and the systematic structure is no change. The only thing they change is the gate driver for this
Yeah.
module. So we are working with the two gate driver company, one in Japan and the other one in the North America. So we provide the total solutions to work with the gate driver manufacturer. So the customer can accommodate the already proven gate driver on top of our module. Some
Mm,
of the customer using three module in parallel operations and the single gate driver master and then three daughter card can implement it and customer can easily design the gate driver circuit. So that's we also provide applications and customer to use much easier to convert the IGBT module into the silicon carbide versions.
I see. Are there reference designs or application circuits that are already provided?
So we didn't officially release it yet,
Mm,
but we are working with the two company as I mentioned, and it will
yeah.
come out pretty soon. Yeah.
Okay.
So yeah.
Okay. Gotcha. Thank you. Um, So I wanted to talk about the sort of timeline, the roadmap here, because I remember we talked during APEC, and you mentioned that the 2.3 kilovolt devices were coming this year alongside the 1.7 kilovolt devices. And the PCIM announcement, it covers the 1.7 kilovolt devices. So are the 2.3 kilovolt devices still on track? And what application is driving that in particular?
Yes. So the power system, the DC link voltage is gradually increasing from 800 volt to 1250 volt up to 1500 volt.
Mm,
So we expecting the 1700 volt silicon carbide MOSFET module can cover up to 1250 volt DC link voltage.
mm,
But end user interest in to increase the DC link voltage up to 1500 volt, they need a 2.3 kV MOSFET
mm,
or 3.3 kV MOSFET. So we are under development of 2.3 kV MOSFET as of today. We expect have an engineering prototype of a module by end of this year. And about Q1, Q2 next year, so we will release the 3.3 kV version. But 3.3 kV version may not use Econo or QSiC Dual3 module. We have a different module platform is preparing for the
Okay,
3.3 kV.
for the 3.3 kV different module. Okay,
Yeah,
gotcha. So it's not going to be dual three. It'll be something else, and that'll probably be coming up next year.
yeah, next year. So
Yeah,
yeah,
exciting.
so both
Yeah,
mhm.
are
Go
the
ahead.
higher voltage, 2.3 and 3.3 kilovolt, are these going to be intended? Are they more intended for the Gen 4 silicon carbide, or are they still within the Gen 3 family?
So actually, we already the 1.7 kV and 2.3 kb, 3.3 is basically Gen 4 technology.
Okay.
So
Okay.
yeah, so we didn't announce the Gen 4 product yet, but you can see here quite significant improvement
Mm,
compared to Gen 3 in LDS on and also the
mm.
switching performance. So
And
it's
that's also planar?
yeah, it's a still planar
Mm,
structure, but figure of merit, RDS on time, QRR, EOSS, and the QG. So it's all performance is improving.
I see.
So actually, generation 4 version, we don't have a 1.7, 2.3 generation 3 version, but
Mm,
the platform is a Gen 4 platform. So
I see. I see.
it's coming. It's
I
coming. So
see.
yeah.
Well, I imagine those are also improvements in edge terminations and cell density,
Oh
as
yeah.
well, right? Yeah.
Yeah, so absolutely. So we have a switching energy improvement compared to Gen 3, Gen 4 here. And yeah, so we
Mm,
absolutely already have engineering samples and customer evaluations of our Gen 4 MOSFET, even to 1.2 kb. Uh, but yeah, it's coming very soon. Yeah,
gotcha.
yeah,
Well,
I
yeah.
mhm.
Please carry on. Sorry.
Yeah, so we didn't officially announce sample MOSFET, but 1.7 kb in the 2.3 kb all Gen 4 platform. And we have a 750 volt, 1200 volt Gen 4 device already in full qualification stage.
Okay. Okay.
Yeah,
Well, if you can stop sharing your screen if you'd like, and
yeah, I tried.
yeah,
I,
there we go. No, don't worry, I don't see it anymore. You're good. Thank you so much for your time, Timothy. Was there anything, any sort of final comments, anything I might have missed that you wanted to cover?
No, so SemiQ is a very exciting to present our QSiC Dual 3 modules in the industry. So we see a lot of interest in AI data center power suppliers. So
Yeah,
either the solid state transformer
right.
or the chiller driver and also the AC/DC converters from line transformer 480 volt AC to
Mm,
800 volt DC conversion. So yeah, we are very excited to offer this solution to the customers. And it also strong interest for the locomotive applications.
mm,
So it's a tram or e-bus kind
mm.
of application customer is express interest to use
Interesting.
these modules. Yeah.
Thank you so much for covering that. I did forget to cover the applications, so I appreciate it. Thank you very much for your time. It was a good chat.
Sure. I really appreciate you give us the opportunity to discuss these technical topics and applications of our new module. Thank you.
Thank you, and thank you for coming prepared with the PowerPoint.